Got a rectangular box. The base is 10 by 15 feet. So that's going to be and the water goes up to a 4-foot level, so it's a pretty short but wide box. So this could be the 4 feet for the water level. This could be the 10 feet, and then we would need to go back by 15 feet. Beautiful 3D perspective. So this is the 10 feet, this is the 15 feet, and that box is full of 4 feet of water. Find the hydrostatic force exerted on one end of the box. Well, I purposely made this a vague question because are we talking about this side of the box or this side of the box? Those are the only two choices because it doesn't say a top or a bottom, it does say one end. The way that I drew it, this is an end and this is a side, but if the person was standing on this side. Anyway, the reason that I made this up slightly vague is so that you don't use both. You don't use both the 10 and the 15 in the setup. So what I'm going to do is concentrate just on this side. I'll find the amount of force that is on this side. One thing I need is a coordinate system. I need to know where to put x and y, so I'm going to say that this is going to be my x-axis, and then right through the middle of it will be the y-axis. So we've got this water level going up to a height of 4. Now the idea is water weighs 62.5 pounds for every cubic foot. So if you have the face of the box like this, and you say, well, what I'll do is I'll take let's say a 1 foot by 1 foot square. The area of that, of course, is 1 foot. And you multiply how much the water is pushing on it. So you say, well, it's that many pounds for every cubic foot, but if I multiply by my 1 by 1 foot squared square right there, what happens is this is now going to be 62.5 pounds per foot, which is a pressure, not a total force. When we get to this, to just be in pounds, then that will be a total force. So how do we get that to be in pounds? Well, what's important on this is if this thing is on that wall and it's close to the top, there's very little pressure on it. If you move it 4 feet underwater, there's more pressure. The farther you move it underwater, the more pressure there is. So then what you've got to consider is how deep is it? So what we would say is, okay, maybe that's 1 foot underwater, maybe that's in the middle and it's 2 feet underwater. So if it was 2 feet underwater, then we would need to multiply by 2 feet, because this is saying there's an additional 62.5 pounds for every foot you take it down. So if I take it down 2 feet, then the feet would cancel and I would have the total pounds. Now that's just for that one little square. Now take that idea, come over here and say, instead of one little square, what I'll do is make one rectangle that goes all the way across, and then calculate how much force in total is on that one rectangle. I can then move that rectangle up and down this whole range and add up all of those using integration, and then we would have the total force. So because I'm using up and down, that's going to be y, so usually this would be called delta x. Right now it's called delta y. So let's see, we would have 62.5 pounds per cubic foot. And then we need to multiply that by the area, which is no longer just a little square, but it's a rectangle. So the area of this rectangle is just its length, which is 10, and its width, which is delta y. There's that part. And then there's this part. Now submerge that thing underwater. And what we've got to do is say, well, if this is the y-axis, then from here to here is called y. But we're not measuring it from the ground. We're saying take this thing and then plunge it underwater. So we need to measure it from the top plunge down, which because this is a 4, this distance would be 4 minus y. So then replacing this idea of plunge it underwater by 2 feet, we plunge it underwater by 4 minus y. Okay, so that's going to be the, so look at this is in feet, feet, feet. So that's feet cube, which would then cancel that feet cube and give us pounds. Now we need to add up all of those such rectangles. So integrate from 0 to 4. The 62.5 times 10, and then this becomes dy when we're talking about integration. So 4 minus y dy. Okay, so this 625 can be factored out, and then we would just have to integrate this, which is going to be a 4y minus y squared over 2. Oh. Okay, I'll just go ahead and say it twice rather than rewrite it. So integrate that, which is going to be a 4y minus y squared over 2. And then evaluate from 0 to 4. So you've got 625 times, let's see, this is going to be a 16 when I substitute the 4. This is going to be a 16. This is going to be a 16 divided by 2. So 16 minus 8. And when you substitute 0 in there, it contributes a 0 and a 0. So 625 times 8, so that would be 5,000 pounds total force on that side. Now if you were to find this side, then the work would be exactly the same, except this would be a 15, and consequently this would be 1.5 times bigger.